Okay, so next we're gonna do this more tricky case of strict turnstile streaming. So before the break, we had just these increments. Whenever we see an item, we just count one more of that item. Now we have these general updates that is changing the frequency of element I by some value delta. Delta can be positive and negative, but for now, the strict turnstile is saying that any frequency will always be non-negative at any point in the stream. So we'll always have a non-negative number of occurrences of any item. And I think at the end, I'll give an example where this is a reasonable assumption. Okay, so we still want to compute these estimates of the frequencies. The frequencies now are just those, I guess, the sum of all the deltas. Let me write it like this. So now the frequency is the sum over all j, such that how do we write it? Let's say maybe all pairs. Maybe let's write it like this: j comma delta I. Is this a good way to write it? Okay, let me write it here. Our stream looks like this. And now I guess the frequency of I is the sum over all j, so that ij is equal to I delta j. So it's just that update up here, right? The frequency is just sum of all the deltas for those that update element I. All the items in the stream that update element I. We want to estimate that. And let me write down explicitly what is the type of estimation error that we want. So what is the quality of the estimate that we're going to get now? Here, as I said, we need to use randomization. And the quality we get is going to say something like this. With probability minus delta, it holds that the estimate we produce is not too much larger than the true estimate, which so there's another parameter epsilon here, and let me write it. I'll define what it is in a second, times the one norm of f. So what is the one norm of f? The one norm of f is just a more general way of counting how many times we see an item. Before we said the stream length was n. Now, you're basically saying that the quantities of the estimate are proportional to some of the absolute values of the frequencies. And here, all the frequencies are non-negative, so it's just the sum of the frequencies, which is before the sum of the frequencies was exactly n. So it's this kind of like before we had an error that's proportional to something times n. Here, we have two parameters that we specify when we want to use this solution. We're going to see when we want to build this data structure sketch. We're going to say, I want this delta and this epsilon. So that tells me I want to say, I can specify how often do I want it to be a good estimate. Right? So delta is really an error probability, and epsilon is an approximation quality. Small epsilon means we want very accurate estimates. Small delta means we don't want it to fail very often. And also has one more guarantee, because it's easy to always, if it was easy if we didn't have any other constraints, we could always just output 0. That would always satisfy that it's less than equal to 2 estimates. Something. So of course we want one more guarantee. And here we're going to actually do something even stronger. Probability 1. The estimate greater than equal to the true estimate. So it's never an underestimate. That is the kind of guarantee that we'll derive at the end. We want to produce an estimate that is always an overestimate, and quite often it's not too much bigger. So the error now is proportional to this epsilon times this one norm. If you remember the Mr. Grease from before the break, there we said that these estimates was the other way around, right? It was always an underestimate. This was Mr. Grease. And then it was not too much smaller The way we wrote it was this n over k plus 1. So the natural way of thinking of, if you want to say, oh, this is something with divided by k plus 1, this is something with epsilon, I think the nice way to interpolate between them is to say, well, Mr. agrees the space budget of k corresponds to an epsilon of 1 over k plus 1. It's kind of the way to interpret it in this different formulation, right? Because the one norm of the frequency vector here, when we're in this simple insertion only, is just the number of items I've seen in my data stream, which is what we call n. So basically, Mr. agrees the error is something like epsilon times the one norm, with epsilon being 1 over k plus 1 when the space budget is set to k. That also means that the space budget of Mr. agrees was order k, which is then order 1 over epsilon if you write it in terms of epsilon. This is what we had before. We're going to now see a different solution that can handle the negative updates, but it's going to be wrong sometimes. But other than that, it's going to be very similar. And the space we're going to aim for is also going to be something that looks like 1 over epsilon. There will also be a dependency on this delta, but we're going to try to aim for something that looks like this. So this is just to put it in context. So, but now we want to give a different solution that can handle these negative things. And again, one can actually prove that you need randomization if you want to do anything other than storing the whole data set. Right? You actually have to use randomization. There has to be a chance of failure, otherwise you cannot solve it. And this can be shown in roll bounds, so we just have to do something randomized. So what are we going to do? Solution we're going to see is called the CountMin sketch. And we're going to start out in a simpler case. We're going to start out by looking at just a case where we say, okay, I'm allowed to fail probability 1/2. We'll just, let's start with, and we only have to worry about this epsilon, then we figure out later how to handle the delta. For now, we just say, okay, I'm allowed to make a big overestimate with probability 1/2, up to 1/2, but no more than 1/2. So this is kind of our goal. And I think one nice thing about this CountMin sketch is that it's extremely simple. And I guess that's a common thing with many of the randomized algorithms we see in the course, right? They're very, very simple to describe the algorithm. They're easy to implement. Analyzing them is more tricky. So what does it look like? Well, we have an array A. This array stores counters, and there are k of them. Just to maybe keep the terminology similar to Mr. agrees, the k counters, and we're going to set k. We can see afterwards why, but for now, let's just accept that this is what we do. We're going to set the k to be 2 over epsilon. So we're going to have 2 over epsilon many counters or entries in this array. To begin with, they're just counters, and to begin with, they're all 0. They just start out as 0. 0 initialized array. And then we're going to use something from last time. We're going to have a hash function h that maps from the universe into this range, into this array. And h is going to be a universal hash function. So what did it mean that h was universal? It meant, I just recall from last lecture, right? It means that for all 2 distinct keys in the universe, which is the weakest sum, the probability over the random choice of the hash function that x and y map to the same is no more than 1 over k. So we saw different ways of implementing such hash functions last time, and they're very efficient implementations of it, and this is just all we need for this data structure. So how does it work now? Well, there are 2 operations, right? There is whenever we see an update, right? So we want to process an update. An update is an index I and the value delta. What do we do? It's very simple. We just say, well, let me hash I, It gives me a counter in this array, and then let me just add delta to that counter. Let me write it like a little bit programming language like. We're going to add the value delta to that counter. That's the full code. It's extremely simple procedure, and here is the estimate. I want to estimate the frequency of I. I just return a index hash of I. I guess you can see the code basically doesn't get any simpler than this. It's a super simple algorithm sketch. To update an item I by a value of delta, I just hash I into some counter, and I add my delta to that counter. So all the updates to a given I is going to go to the same counter, right? Because if I evaluate the hash function again, I'm going to get the same entry. And when I want to estimate it, I just return whatever's in that counter. Of course, you can see this doesn't give exact results because, let me have this for example here, right? Maybe we update 1 with a count of 3, maybe we update 2 with a count of 1, and maybe we have 4 with a count of 2. We have this array here. Then it could be the case that maybe the hash of 1 is equal to the hash of 4. So they map to the same entry. And then when I'm processing this stream of items, I'm gonna first increment it by 3, and then maybe 2 hashes somewhere else, maybe hashes over there, and then I get another 2 here. So now it's gonna be a 5. Now when I estimate the frequency of 1 or 4, I'm gonna get the same value 5. Right? So I'm clearly not counting exactly, but that's also okay as long as my estimates are not too far off from the true estimate. And okay, so we want to argue now that this solution has these 2 guarantees. The second one is the easiest one to argue. So with probability 1, we want to say the estimate is at least the true frequency. Why is that the case? Yeah.
For a given element, we will always implement the same subtlety array.
Yes. What about this one? We could also have negative updates. Okay. So what are we using here? We can actually have both positive and negative deltas. And we have an assumption that helps us here. So these updates can be both positive and negative. Yes, we say they're bounded by in some range from minus m to plus m. Say we did make one assumption. We're studying a slightly restricted version. Yeah.
Yeah. So it's frequency could be positive.
Yes.
And you got like that same.
Yeah.
Then it's like the whole frequency.
That's exactly right. So, right, we have this promise. So maybe that the stream has this property that can have negative updates like here, but you always promise that any item, its frequency, so that's the sum of all the updates that has appeared to this item. That thing is always non-negative. So the sum of all the updates to any given item is always non-negative, which is the case here. So now this would be updated to 4. So you can subtract something from the count of 4, but it never goes negative. Which means that when I want to estimate an item, for instance, the frequency of 1, I go to this item. The things that are stored here is my frequency, because all my updates go to this position, plus the frequencies of everyone else that hashes to the same, but they are all non-negative, right? So it can only get bigger by having collisions with others. Right. So that is why we are never going to underestimate it. This is actually going to be very important next time when we go to some of these heavy hitter solutions, this more complicated problem where we want to find the frequently occurring items. We're going to use this property very heavily. Well, of course, the other one is, can we show now that estimates are often not too large? Right, that's the trickier part. This is where we have to do some work. We want to argue that we don't overestimate too much. And for now, we're going to look at this simple case of a failure probability of 1/2. So I want to say with probability at least 1/2, so maybe let's say with probability, to make it clear, with probability at least 1 minus delta. So with probability at least 1/2, it should be the case that the estimate we produce like this is no more than epsilon times 1 norm off from the true. And the 1 norm was the sum of all the frequencies that are being stored. So let's try to see if we can prove something like that. So to do that, maybe we could start by writing out what is this estimate in terms of some random variables. Right? So that gives us something we can analyze. So what is the estimate that we're going to produce for a given I? Well, as we can see on this illustration, right? What we're going to do is we're going to return what is in the, so maybe we can write it like this. It's going to return a I. What is the value here? Well, we know that all the updates to I go there. Right? So it definitely contains the frequency of I, but then it also contains the sum over all j's not equal to I, such that hash of j is equal to hash of I, frequency of fj. Right? Does that make sense? Right? It contains all the other ones that hash to the same. This is what I get. And we would somehow like to analyze this. Maybe introduce some random variables. I guess these are random. I guess this is summing over a random set of indices. Right? It's summing over the set of indices that you're summing over depends on the hash function. We would actually like to rewrite it as just a sum of a fixed set of random variables. It's always the same set of random variables we're analyzing, but then we could use maybe some things like linearity expectation and so on. A sum over a random set of indices is perhaps a little bit harder to deal with. So let me rewrite it a little bit here. So let me keep the frequency of I. You can also say, let's just sum over all j's not equal to I, everyone. And maybe we could write it like this. We could say, let's define, I guess we could call it, let's write it like this, an indicator random variable for the event hash of j is equal to hash of I. And I'll write out what that means in a second, times fj. So whenever we write something like this, and then a Boolean expression down here like hash of I is equal to hash of j, we really mean the random variable taking the value 1 if this happens, 0 otherwise. Does that make sense? So I'm just introducing a random variable here that takes the value 1 if they hash to the same. And now I can sum over all the items in the data stream. Right? So the frequency estimate that I'm returning is the true frequency plus the sum over all items in the data stream, indicator for whether they hash to the same, times the corresponding frequency when they that item has. So this is what we're going to return. Okay. Now, what is it we want to know? Or we want to bound? We want to bound the probability that this estimate is, we want to say it's unlikely that this estimate is more than the true frequency plus epsilon times 1 norm. And this is what we'd like to add. So what we can see is that the mistake we're making is really this part here, right? This is our mistake or excess estimate. Let's call it X. This is the excess that we have. And what is it we want to know? We want to bound what is the probability. The random thing is the hash function, right? When do we have a mistake? We have a mistake if this X here, the mistake, the overestimate, is bigger than epsilon times this 1 norm, right? This is the mistake. This is precisely when we have a mistake, right? Because in this case, our estimate is the true frequency plus something that is too large. So this is what we'd like to bound, this probability here. So what tools do we have for bounding something like this? Looks like something we've seen. Yeah. Markov's inequality is a good choice. And what do we need to check for Markov's inequality? What are the requirements on the random variable for us to use it? And one more. It's both discrete and there's one more requirement for Markov's. Yeah.
The random values are
No, it's not. Yeah, there's only, yeah. It has to be non-negative. Yes. Yeah. Markov's inequality requires non-negativity. Yeah? So Markov's. So here for us is that for non-negative x, random variable x, for all t, the probability x is greater than t is less than the expectation of x, the formulation that we saw. So we need to check this non-negativity of our random variable. Is this a non-negative random variable? One here. Yeah, some are nodding. Why is this a non-negative random variable? What do we have that promises us this is non-negative? Yeah. Yes, with the frequencies are non-negative when we're in this strict turnstile setup. Right? So let's here again we're using them in the strict turnstile setup. This is non-negative. This is 0, 1 random variable. This is also non-negative. So this is a non-negative random variable. We are allowed to use Markov's inequality. So we can just now plug in, right? It has the right form. So then this is going to be less than the expectation of x over epsilon times the 1 norm of frequency vector. Okay. So, okay, now we can see what do we need to know. We need to compute the expectation of x. This is what we have to do. So let's do that. X is this expression here, right? So expectation of x. Expectation of sum for j not equal to I. Have this indicator hash of I is equal to hash of j times j. Okay, what do we do when we have an expectation of a sum? So yeah. Yeah, we use the narrative expectation, right? So we can move the expectation into the sum. Furthermore, this is just a constant, not random. So we can move it all the way in here. So the sum over j not equal to I, just fj times the expectation now of this indicator random variable for hash of I is equal to hash of j. Okay, now this looks like things we've done before in this course, right? Whenever we have the expectation of an indicator random variable, these are easy to analyze the expectation of I because they are 1 times the probability it's 1 plus 0 times the probability it's 0. That's the expectation. So the expectation is just the probability it's 1. This is the indicator for hash of I equals hash of j. And what I get is sum now over j not equal to I. And I get fj. And I get now the probability that hash of I is equal to hash of j. Yeah. And what do we know about that probability? Yes.
Our hash probability being universe. So 1 over m b.
Yes, exactly. Right. We chose our hash function to be universal. This property we covered last time, right? That for any two distinct keys, the probability they hash to the same is at most 1 over k. We're summing over j not equal to I, so these are two distinct keys. So this probability is at most 1 over k. This is less than equal to the sum for j not equal to I fj over k. This. And this is of course less than equal to if I sum over all the values of j, so the 1 over k, and sum over all the j of j. Here I'm again using non-negativity of the frequencies. I could maybe add an absolute value if I wanted to. This one here is exactly one norm in particular because my frequencies are non-negative again. So this is equal to one norm of f, sum of all the frequencies divided by k. That makes sense? So now I have my expectation here, and I can insert it up there, and then I get less than equal to. Inserting this frequency up here cancels out with the one norm cancels out with the one norm, and then I'm left with 1 over epsilon k. And then I knew how to choose k. I kind of said, okay, let's choose k to be 2 over epsilon. So if I insert 2 over epsilon here, I get 1/2. It's because k was chosen to be 2 over epsilon. I guess this is also how you can figure out that 2 over epsilon is a good choice. We wanted the error probability to be 1/2. We see here the error probability is 1 over epsilon k. So this choice of k makes the error probability 1/2. So then the chance that you are overestimating by more than epsilon times one norm is at most 1/2. This all follows just by Markov inequality, linearity of expectation. Let's move it up. So now the question is, what happens now if we want a better delta here? Or maybe also just quickly see what was the space usage. It was 2 over epsilon many counters. So similarly to this Mr. Grease, the space usage is like order 1 over epsilon. So the space usage is actually kind of optimal as well for this value of failure probability. We want to prove that. Well, how could we now, let's say I want now to handle the more general case. I want maybe a small, very small failure probability delta. Maybe I don't want it to be 1/2, but I want it to be correct much more often than half the time. So what would be the quickest fix to what we've done so far if I wanted a failure probability of only delta? What could we do here to modify it? The easiest, maybe not the optimal way to change it, but there's something that works. If we wanted to, yeah.
Change k to be 1 over epsilon.
That's exactly right. An easy fix would be to say, let's try to change k to 1 over epsilon delta, right? Because then this 1 over epsilon k becomes just delta. That makes sense to everyone? Then and that works. We already showed it, right? It's just the same analysis, except here you get delta. The space usage now becomes proportional to 1 over epsilon delta, which is okay, but you can do much better, it turns out. So right now we have a solution now using order 1 over epsilon delta space. What the lower bound says is you need, we're not going to cover it, but there's a lower bound saying you need the space to be at least 1 over epsilon times log 1 over delta. That's the lower bound. And what we're going to see now is you can also match this lower bound, right? So it's possible to actually only pay log of 1 over delta instead of 1 over delta, right? So it's a much better dependency on the failure, an exponentially better dependency on the failure probability. Here it's 1 over delta, here it's log 1 over delta. Makes sense? So we can drive down the failure probability much faster without paying that much in space. So we're not gonna do this. We're not gonna increase the array size like that. We're gonna do something different. So what we're gonna do now, it's a very simple modification to what we have. And so we remember H is universal. So let me update the picture here in the middle of how we're gonna solve it now for general delta. So what we're going to do is we're gonna, instead of having one array A, we're gonna have T arrays. They're all gonna have the same size as before. And what we're gonna do is we're gonna set this T to be log base 2 of 1 over delta. So we'll see that this is a good choice. What do we do now? We have now not one hash function, but T hash functions. They're all still just universal hash functions. And they all still just map from the universe into K, into an output size K. And we pick the random seeds, these hash functions, independently of one another. Right? Use new random bits to pick the random seed for each of these hash functions. They're chosen independently of one another. How do we update it now? Very simple. So what we do, we just say for j equals 1 to t, we go to the jth array, we use the jth hash function on I, and then we add delta to that entry. Makes sense? So basically we're just repeating the data structure from before t times. So we're just building t copies of the data structure from before. We're just going to update all of them. We're going to go through all of them, use the hash function that belongs to this data structure to map into an array and add the value there. And to estimate, let's see, so basically now when I see an update to an item, I'm going to hash my item here, I'm going to hash it here, I'm going to hash it here, I'm going to hash it here, and I'm going to add my value delta to all these entries, right? That's how we're going to do it now. This is, puts a separate row sheet. I'm going to add in all these places. Now, what seems like a good strategy for estimating now when we do like this? Build T data structures, I hash it in all of them, I add my value to all of them. How should I estimate the frequency of I now? Yes.
Take the smallest.
We take the smallest, yes. And why the smallest?
That's turnstile. Cost.
Yes.
So every time there's a collision.
Exactly. Yes. So we have this kind of like we're always over, all the estimates always overestimates. So we might as well, best thing to do would be to take the smallest of all these counters. That's the one with the least error. So, and that's also where the now name CountMin comes from. So we're going to return min over j, a j hash j I. That's the full solution. Okay. So let's try to see if we can analyze this one. So we already know, right, from the analysis up here, that one of these structures, the estimate here, the probability that this estimate is too big is at most a half. Right? The probability that it's larger than epsilon times 1 norm is at most a half. What now? What can we say here? The probability now that, so really when we're returning the minimum, we'll only overestimate if all of them overestimate. Does that make sense? When we're returning the minimum value. So the probability that our estimate is larger than the true frequency plus epsilon times 1 norm is basically the probability that for all j, should we write it? Should we call it the estimate of I given by a data structure j? Maybe I hope you know what this means. It's just the estimate that the jth array would produce is larger than I plus epsilon times 1 norm. Make sense? They all. So what is the probability now that all of these T data structures overestimate by too much? Can you say something about this? You know, any one of them fails with probability at most a half. What's the probability that they all fail? Yeah.
hash functions random.
Yes. Exactly right. We choose, and this is important, we choose the random seeds, the hash functions independently of one another. So all these events are independent, and the probability that they all occur is the product of the probabilities that each of the individual ones. So this is equal to the product from j equals 1 t probability that the jth estimate here is large. So this is really using that I pick the random seeds to my hash functions independently of one another. You can also see, like, if I didn't pick it independently, I pick my seed for the first one randomly as I'm supposed to, and then I copy the seed to all the others. Then, of course, one fails if they all fail. Right? So it's important here that you initialize them independently. Initialize the hash functions independently, then this probability is just the product of the probabilities. All of these happen with probability at most a half, right? So this is 2 to the minus t. What t did I pick? I picked this t here, right? So this is 2 to the minus log base 2 of 1 over delta. Now, minus this log is the same as minus 1 times this log, so I can move that into the log, into the exponent, right? So it's like 2 times log 2 of 1 minus delta to the minus first, which is just delta, right? So it's 2 to the log 2 of delta. It's just so by picking just a logarithmic number of these, constructing a logarithmic number of copies of this data structure independently of one another, I can make the failure probability go down potentially faster than how many I'm picking, right? Because they all have to fail, and this happens independently of one another. I think this trick we'll see, yes, many times in the course as well in randomized. It's a very standard trick in randomized algorithms. Start by solving a problem with failure probability like a half or a quarter or something, and then just run the algorithm independently a bunch of times, and hopefully either in this case you can just take the minimum and that will work. Then they all need to fail for the whole algorithm to fail. Sometimes you have to be a little bit more smart. We'll see that in the last example today. We cannot because we're really using this, and we never underestimate. So we can return the minimum, and then they all need to fail for the whole thing to fail. We'll see next one that can both overestimate and underestimate, but you can still do a trick similar to this minimum and do independent copies to do something nice. You just have to do a different trick that we'll come back to. Okay, I think this is a good place to stop and have a break. So yeah, but this is the CountMin solution. It has this space use is really 2 over epsilon columns, really, if you will, and log 1 over delta rows of counters, and this code is really just these couple of lines of code to get these estimates. So let's have a short break now.